Hi, welcome back to the AICE Chemistry lecture series. We're going to look at Chapter 5, Section 5 today, the last section of Chapter 5, which focuses on fullerenes. Now, fullerenes are very specific allotropes of carbon that are very modern and have a specific place in research. So let's get started. Carbon allotropes are both synthetic and natural. There are other carbon allotropes other than the graphite and diamond that we saw in the earlier section. Diamond and graphite are the only naturally occurring allotropes of carbon, but there are some man-made synthetic allotropes which we call fullerenes and graphene. Fullerenes and graphene are the most important synthetic allotropes of carbon because we use them in modern technology. Allotropes of carbon that form hollow spheres or tubes out of carbon structures are what we call fullerenes. Fullerenes are formed by forming these ring-shaped structures, usually either hexagons or pentagons, and then forming different giant structures or bigger structures from them. Most fullerenes fall into the classification of nanoparticles. Now, nanoparticle technology and nanoparticle research is very important and hot topic today in science and chemistry. And nanoparticles are essentially any particle whose size is in the nanoscale range, usually between 0.1 and 100 nanometers. So, spheres and tubes made out of carbon that fall into this nanoparticle range are what we call the fullerenes. So let's talk about the fullerenes first, and then we'll talk about the other allotrope, which is graphene. Buckminsterfullerenes are a simple molecular structure type of carbon which forms these little spheres. So you can think of Buckminsterfullerenes as little soccer balls made out of carbon atoms. The molecules have this soccer ball shape because they're formed by connecting pentagons of carbon with hexagons of carbon. Now, these structures are arranged into very specific shapes. The most common Buckminsterfullerene is the C60 Buckminsterfullerene, and it was the first one discovered. The C60 Buckminsterfullerene is named C60 because it has 60 carbon atoms, which form 20 hexagons and 12 pentagons in total. The bonds are all covalent bonds, and they are made to form this sphere. Some of the carbons in the Buckminsterfullerenes can be omitted to form smaller Buckminsterfullerenes than C60, like C36 and C20, while we can also add more pentagons and hexagons to form something like C70. Now, you cannot make a Buckminsterfullerene out of any combination of carbons. There's only very specific numbers that will give you these hexagon and pentagon shapes: C20, C36, C60, C70, so on and so forth. Some of the carbons in these shapes, or actually all of the carbons in these shapes, are going to be sp2 hybridized. So Buckminsterfullerenes have carbons that are sp2 hybridized, which means all of these carbons have a loose p orbital. Just like we discussed with graphite, there is an area of the localized electrons above and inside a Buckminsterfullerene. Because the carbons are sp2 hybridized, they have those p orbitals that stick out and can form together to create the localized area of electrons. Now, unlike graphite, however, Buckminsterfullerenes do not conduct electricity. The main reason why we're going to discuss in the next slide is because the spheres act like separate particles. So let's talk about the different properties, because by having these little spheres of pentagons and hexagons of carbon, we can have a lot of different and really cool properties to Buckminsterfullerenes. Buckminsterfullerenes have very different properties than most of the other allotropes of carbon. First of all, Buckminsterfullerenes, each individual soccer ball acts like a separate particle. So we had Buckminsterfullerenes, what we have is a bunch of little separate C60 or C20 or whatever Buckminsterfullerene we have, particles of Buckminsterfullerenes. That's why we call them nanoparticles, because the size of an individual little soccer ball is below that 100 nanometer threshold. So because we have these individual little soccer balls, Buckminsterfullerenes end up acting or behaving like individual little particles. Even though each individual particle is held together by covalent bonding, they are really weakly connected, because since they're completely made out of carbon, the only thing holding one little soccer ball to another are very weak London dispersion forces. Those London dispersion forces make it so that Buckminsterfullerenes don't melt, they sublime. They are going to go straight from the solid state to the gas state. They have very low sublimation points. They turn from solid to vapor when heated to just about 600 degrees Celsius. Now, you might think that that's not a low temperature, but when comparing it to the melting point and boiling point of things like graphite and diamond, that's actually a pretty low sublimation point. This is due to the very weak London dispersion forces that are holding the individual particles to each other. Because of that, they're also very soft. They're soft because it takes very little energy to break the intermolecular forces when holding the particles together. And so when you feel the Buckminsterfullerenes, they break apart very easily, creating that soft texture. Now, even though they have the localized area of electrons, Buckminsterfullerenes are not conductive of electricity. They're poor conductors. And that's because even though an individual particle has the localized electrons, the particles cannot communicate with each other to give off that electricity. So they can hold the electricity within themselves because of the localized area of electrons, but because they're so far apart and they behave like individual little particles, they cannot communicate the electricity from one little soccer ball to the next. So we say the Buckminsterfullerenes are poor conductors of electricity, even though they have the localized areas of electrons, because they're confined to each individual particle. Now, this one's a little niche. It's a very specific property, but Buckminsterfullerenes have slight solubilities in disulfide and methylbenzene. So they're not soluble in water, but they are soluble in disulfide and methylbenzene. The individual particles are soluble in these because both disulfide and methylbenzene are non-polar. Both this and this are non-polar solvents. Just like our Buckminsterfullerenes. Their individual particles are soluble because the force of attractions they form are very similar. Unlike graphite and diamond, which are giant covalent structures, the Buckminsterfullerenes are considered to be simple molecular. And by being simple molecular structures, their solubility depends on their polarity. Since Buckminsterfullerenes are nonpolar, they dissolve in nonpolar solvents like disulfide and methylbenzene. Now, the last property of Buckminsterfullerenes that we have to discuss is their reactivity. They are really highly reactive. They're really highly reactive because they have a high electron density. Because of those delocalized electrons we talked about, that is what gives them their high electron density, the delocalized electrons. The delocalized electrons give them a high electron density, which means that in certain areas the particles have way more electrons that they need, and so they become very reactive. Remember that chemical reactions are just us shuffling electrons around. And because it's just the shuffling of electrons, and because the localized areas of electrons have a high negative charge, they're going to attract positive things to react with those Buckminsterfullerenes. And so Buckminsterfullerenes, thanks to their high electron density due to the delocalized electrons, are going to be really highly reactive. So that's the first of the fullerenes that what we talked about, right? These Buckminsterfullerenes, which are these little sucker balls made out of carbon. And they come in different types based on how many carbon atoms they have. And these little sucker balls have the localized areas of electrons because all of their carbon is sp2 hybridized. And because of that, they have these properties. Low sublimation points because the only thing holding one sucker ball to another, one Buckminsterfullerene particle to another, is weak intermolecular London dispersion forces. They're soft because of the same reason. The London dispersion forces are easy to break. They're poor conductors because even though they have the localized areas of electrons, they do not communicate with each other, that the localized area is confined to each individual little particle or sucker ball. That does, however, the delocalized electrons gives them this high reactivity because the individual little sucker balls or particles are going to be very reactive because of the localized electrons giving them high electron density. And they're highly soluble in disulfide and methylbenzene because they're considered to be simple molecular structures which are non-polar in nature, and so they will dissolve in non-polar solvents like disulfide and methylbenzene. The other fullerene that we're going to talk about is nanotubes, or our nanotubes. Nanotubes are created from hexagonal carbons, so carbons that are hexagonally bonded, arranged in a cylinder. So very similar to graphite, nanotubes have these carbons that are sp2 hybridized, creating these hexagonal shapes. Now, the difference is that instead of having different layers like in graphite, nanotubes are one layer of these hexagons that are wrapped around into this tube shape. I gotta do a better job of that. Into this tube shape. So these sp2 hybridized carbons that are organized, covalently bonded in these hexagonal shapes, are wrapped around into a tube or a cylinder. Now they have very special characteristics, a lot of them very similar to those of graphite. Now they have high electrical conductivity, but only along one axis. The carbon nanotube also has delocalized electrons because the carbons are sp2 hybridized. Again, same explanation. They have those p orbitals on the carbons, and those p orbitals are going to merge together, forming areas of the forming the localized pi bonds all over the nanotube. Every single carbon is connected to the next carbon through a delocalized area of electrons. And because it's delocalized electrons, they're mobile, charged particles. Meaning the electrons can move all throughout this tube. They're mobile. They're charged because they're electrons, and they're particles because they're electrons. So, because of that sp2 hybridization of the carbons forming these hexagons, we have this delocalized area of electrons, giving nanotubes high electrical conductivity, but they only conduct electricity in one axis, meaning that electricity is conducted through a nanotube in the long axis. Why? If the electricity goes like this, it's just going to get caught in a loop around the tube. So nanotubes conduct electricity in one direction. It makes the inside and the outside of a nanotube a giant pipe of delocalized electrons. And that is actually very useful for current technology to create these tiny little wires, nanoparticle wires of nanotubes that can conduct electricity. Nanotubes also have a very high tensile strength. Now, tensile strength is the ability to withstand being pulled. And they have very high tensile strength because of the strong covalent bonds. If I grab this nanotube and I pulled it in two separate directions, so I grabbed one end and I pulled it this way, and I grabbed one end and pulled it this way, I will have to pull with enough force to break it, to break all the covalent bonds holding the carbons together. That takes a lot of strength. Remember, covalent bonds are really, really strong. And so it takes a lot of force to break a nanotube. By pulling. They have high tensile strength. And finally, due to those strong covalent bonds as well, they have very high melting points. Due to the strong covalent bonds throughout the whole structure, we require a lot of energy to break these covalent bonds and therefore melt a nanotube. So those are the three most important properties of nanotubes. They have very high electrical conductivity along their axis because of the delocalized electrons created by the sp2 hybridized carbons. They have high tensile strength because it takes a lot of energy to break the covalent bonds holding the nanotube together. And they have very high melting points because it takes a lot of energy to break those carbon bonds as well. Heat energy in that case. So you can think of a nanotube as a single layer of graphite that has been wrapped around into a tube shape. Finally, the last allotrope of carbon we need to discuss that is not a fullerene, because only fullerenes are Buckminsterfullerenes and nanotubes are fullerenes. The last one we gotta discuss, which is not a fullerene, is graphene. Now, graphene is also man-made because it is a single isolated layer of graphite which is not completely rigid and can be distorted. So what is graphene? It's a single layer of graphite. So if we go back to the graphite slide, we remember that graphite from the last video is individual layers of sp3 hybridized carbons bonded in this hexagonal pattern. But the layers of graphite are connected to each other through London dispersion forces. Well, graphene is what happens if we isolate one single layer of graphite. If we break off one layer of graphite from the rest of the graphite, we call that singular layer of graphite graphene. It has very similar properties of those of graphite, but they're a lot more exaggerated because there's no other layers of graphite to interfere. Graphene is extremely reactive because its delocalized electrons are now exposed to the elements. They're not sandwiched in between layers. They become these hotspots for reactions to happen because graphite is exposed to only one layer. It burns at really low temperatures because of its high reactivity. It can react with oxygen very easily because of those delocalized electrons that are exposed, and so it burns really easily. It is extremely strong when it comes to mass to strength ratio. Now, what do we mean by that? We obviously could not stand on a single layer of graphite because our mass, our size compared to the graphene is very, very different. But for its size, graphene is really strong in its mass to strength ratio. And that's just because it's essentially a net made out of covalent bonds. It's a sheet of graphite, so a graphene is a singular sheet of graphite, so it's a hexagonal net of covalently bonded carbons. And so it takes a lot of weight or force to break those covalent bonds, giving it extreme strength. And finally, just like graphite is electrically conductive and thermally conductive, graphene has an extremely high electrical and thermal conductivity. The delocalized electrons act as conductors of both heat and electricity in this net, allowing it to conduct electricity just like we saw with graphite. But because it's a single layer, that's a lot more exaggerated as it can conduct all along the net of graphene. And that's it. Graphene is very simple because it's just graphite but isolated, so it's a lot more extreme version of graphite. It is man-made because it does not usually happen in nature. We have to isolate that layer ourselves. But that is the last of the allotropes of carbon we're going to see. So just to recap, we saw that we have what we call the fullerenes, which are allotropes of carbon that form either spheres or tubes. And those fullerenes are the Buckminsterfullerenes, which are these soccer ball-shaped spheres with very specific properties. Then the other fullerene is a nanotube, which is essentially a layer of graphene just wrapped into the shape of a tube, which is also fullerene. And then there's graphene, which it is an allotrope of carbon, but it is not a fullerene. And they all have their own very specific properties. That is it for chapter 5. Thank you for joining us. We will look at chapter 6 in the next video, and we'll start this section on thermodynamics.